So I hope everyone can see that.
Yes. Yes.
So thanks very much for the opportunity to give this talk, for the invitation and the introduction. And it's great to be able to connect with people across continents like this. So I will be talking about traveling waves with multi-valued height. So this is joint work with several people. And it's work over a period of years with several people. So it includes work with Benjamin Akers, my longtime collaborator who's at the Air Force Institute of Technology in the US, Kevin Pond, who had been at Air Force Institute of Technology for a few years. There's joint work with Walter Strauss from Brown University, and my former PhD student, David Sulan, who was at Drexel and then at the Penn State Medical Center as a postdoc. He's moved on to work in industry since then. And with my longtime collaborator and colleague, Doug Wright at Drexel. So I'll just start talking briefly about traveling waves. So traveling water waves have been studied for hundreds of years now. There's a long, rich history of theory of traveling waves in free surface fluid dynamics. A lot of the work, so I'm not going to try to describe hundreds of years of theorems on existence of traveling water waves, but there is actually hundreds of years of theory out there. Now, there's very typically a restriction that we want to get around, and that's the subject of this talk. If x is the horizontal spatial coordinate, then the height of the free surface is usually taken to be eta of x minus ct. So, you know, with it being a evolution problem from physics, of course, you need not just a position variable, but also a velocity variable. So another quantity such as the velocity potential on the surface is also taken, and it would be a function phi, again, as a function of x minus ct. So the fact that the typical formulation of traveling water waves is in terms of functions of x minus ct, the first thing that implies, kind of fundamentally, that implies that the quantities are functions. So eta has to be a function, and in particular has to be single valued in the overwhelming majority of works on traveling water waves. So that means that the height of the free surface is a graph. The height of the free surface is restricted to be a graph or to have single valued height. But we know that that's not always realistic. We know that there are contexts where single valued height is natural, and there are other contexts where single valued height is an artificial restriction. So if you're talking about pure gravity waves, you wouldn't expect traveling waves which do overturn, which do have multi-valued height. But if you are talking about capillary gravity waves, the capillary action can keep the wave in permanent form even if the wave overturns. Okay, so we're gonna proceed towards two goals here. One is proving the existence of traveling waves with multi-valued height, and the other is kind of a softer goal, which is allow for waves with multi-valued height in general existence theories. So sometimes we'll prove that they exist. Other times, even if we're not sure that they exist, we will at least allow for the possibility of traveling waves with multi-valued height in general existence theories. Okay, and this is motivated by a family of special solutions, the Crapper waves. So why are we concerned with proving the existence of traveling waves with multi-valued height? It's because we know they exist. We know they exist because Crapper was able to write down a formula for them. So Crapper waves are a family of exact traveling capillary water waves on infinite depth. Here I've given a formula for them. Theta would be the tangent angle. Theta q would be the tangent angle that the interface forms with the horizontal, subject to a certain parameterization. And so you can give a formula for theta q of the coordinate along the wave a is the real part of omega of e to the ia, where omega is the function omega of z equals 2i log of 1 plus az over 1 minus az. And Q is a number, a real number greater than or equal to 1. And A can be solved for, the capital A can be solved for through the relation Q equals 1 plus A squared over 1 minus A squared. So these solve the traveling wave equation, which I've written here as F of theta, and theta being the unknown, and P and Q being the gravity and surface tension parameters. F of theta PQ is e to the 2 Hilbert transform of theta d h theta dA, and so on. I won't read the whole equation, but all that equals 0. And a very, very good exposition of these waves is in the book on traveling water waves by Okamoto and Shoji. So these Crapper waves satisfy this traveling wave equation when the gravity parameter satisfies P equals 0. So these are pure capillary waves. Q is a surface tension parameter, P is a gravity parameter. This family of waves for Q greater than or equal to 1 satisfies this equation when P is 0. And then these have been extended in some cases, such as Kinnersley extended these to cases of finite depth. So that means that Kinnersley was able to write down a corresponding formula. So there's different special functions involved, but you have a exact formula for them in the case of finite depth. And so the Kinnersley waves, again, are pure capillary waves, gravity equals 0. Okay, and here's a picture of a family of Crapper waves. So at small amplitude, so these are all different waves. At small amplitude, you see it's almost horizontal. Then you get some sinusoidal structure kind of at the intermediate range. And then the black line here is a more extreme Crapper wave. And you can really see the multi-valued height there. You see that this forms a bulb in the middle. And if you were to draw a vertical line close to the middle of that minima, you would see it would intersect the wave surface 3 times. Okay, so these are standard waves of multi-valued height. So if you have a special solution like that, if you have a special solution like pure capillary waves, something that I always want to do with it then is perturb it to make it less special, perturb it to allow for additional effects. So we want more general waves than just pure capillary waves, and we're going to do this by the implicit function theorem. So we know that we have solutions of this equation when P equals 0, and so we want to know about solutions when P is not 0. So we can do that by the implicit function theorem, and what we need to know about for that is the linearization gamma of that mapping F. So we need to linearize about a Crapper wave. And again, this actually was not a lot of effort for us to do because the book of Okamoto and Shoji has so much information about the Crapper waves and the linearization of the mapping. So the linearization gamma, we need it to be a bijection between some function spaces. And Okamoto and Shoji include information about this, that when you linearize, the linearization is injective but not surjective. So we can do a kind of Lyapunov-Schmidt decomposition then. I don't think as far as I know, the Lyapunov-Schmidt decomposition isn't exactly used in this situation where it's injective but not surjective, but it's basically the same idea. We decompose the target space into its range plus what is missed. Okay, so this we say this is the surjective analog of the Lyapunov-Schmidt decomposition. And so applying the implicit function theorem with this kind of Lyapunov-Schmidt decomposition, we get the following result. For all Q greater than 1, there exists a P, which is a function of Q greater than 0, and a C infinity function, theta, such that F of theta of P and P and Q equals 0. And also theta Q of 0 is the Crapper wave, lowercase theta Q. And we have some some structure on them that theta q of p is an odd function of A and smooth with respect to Q. And so in this second figure, the figure on the right here, the sigma is the gravity parameter. And so sigma equals 0 is marked with a vertical line. Those are the pure Crapper waves. And then we were able to extend this to both positive gravity, but also, interestingly, negative gravity. There's, the implicit function theorem. The implicit function theorem gives you a result for parameter values in an interval. And so we get an interval around 0, and that means we get positive and negative values of gravity. And if you compute the negative gravity one, so of course the negative gravity is a little funny, from a physical interpretation, but if you want to think of having, a massive fluid above a vacuum, then that's where the most interesting waves actually occur. The highest amplitude wave comes with small negative gravity. It's marked with a star here on this figure on the right, and this is the graph of it on the left. This highest wave actually has additional symmetry. It's not just odd. It has an additional reflection, kind of reflection shift symmetry. Okay, so you can extend the Crapper waves by more than just gravity. Our paper on this came out about the same time as a paper by Deboek, and Deboek included non-zero constant vorticity also. Since then, Cordoba and Cizo and Grubik in a couple papers have included a non-zero density for an upper fluid. And I say non-constant vorticity seems likely to generate such waves as well. So you do expect features like vorticity and surface tension both to allow for these overturning waves. Okay, so I said that we had two goals. One goal was to prove that more general than Crapper waves, waves more general than Crapper waves can have multi-valued height, and we've done that then. The other thing we wanted to do was to formulate the traveling wave problem so as to allow a traveling wave to have multi-valued height. So if you don't do that, if you include single valued height in your formulation, then when you look at a global bifurcation theorem, you might have an artificial end of your curve of solutions if the waves are starting to become multi-valued and your formulation doesn't allow that. So we want a formulation for a global bifurcation theorem which allows the waves to be multi-valued. So this has been done in 2D in a few papers by other authors using a conformal map, but the conformal mapping approach is fundamentally 2D, and we'd like an approach which can extend to the 3D case and can extend in a straightforward manner to the 3D case. So that's what I'll talk about here. We're going to give this approach allowing multi-valued height. It is going to be for the 2D case, but it can be extended to the 3D case. And we will use the formulation for a global bifurcation theorem. Okay, so I'm going to consider here interfacial flow. So two fluids here, an upper fluid and a lower fluid, infinitely deep, horizontally periodic, and separated by a sharp interface. Each fluid has its own density. So fluid 1 has density ρ1, and fluid 2 has density ρ2, each of which is constant. And the velocities are given by the irrotational incompressible Euler equations. Surface tension is going to be important in what we do. I mentioned before, you wouldn't expect traveling waves with multi-valued height without surface tension. So surface tension is going to be important for this. Surface tension enters through the Laplace-Young jump condition for pressure. Jump in pressure equals tau times kappa. Tau is the surface tension coefficient, and kappa is the curvature of the interface. The initial value problem with surface tension is well posed. That was my thesis. Without surface tension, the problem is ill posed, and there are a bunch of demonstrations of that. Kaflish and Orlana, Lebeau and Komatsky, Wu. except in the water wave case. It's well posed again if ρ2 equals 0. And so this is just some background on this interfacial problem. And Howell, Grubb, and Shelley introduced a numerical method for the efficient numerical solution of the initial value problem for this vortex sheet with surface tension. And the analysis that I do is very much influenced by this numerical method of Howell, Grubb, and Shelley. So we're going to follow their ideas to an extent. The method begins with the formulation of the problem using geometric variables related to the curvature. So we're not going to study Cartesian coordinates. We're going to stick with, as we did in the Crapper waves, we're going to stick with tangent angle. Unlike the Crapper wave here, the parameterization we'll use will be arc length. So we're going to stick with arc length and tangent angle as our dependent variables. Okay, so I'm going to go through the Howell, Grubb, Shelley formulation briefly. So the interface between the two fluids is x of alpha t, y of alpha t. So this is a parametrized curve. The Cartesian coordinates are x and y. X and y are both functions of two independent variables, alpha and t. Alpha is the variable along the curve, so the spatial coordinate along the curve, and t is time. And so this interface moves with some velocity, normal velocity u, and tangential velocity v. So n hat here is a normal vector to the surface, t hat is a tangent vector to the surface. So we have the time derivative of the position xy is u times the normal vector plus v times the tangent vector. So we have these Cartesian coordinates, but that's not what we're going to use. We're going to switch to the tangent angle and arc length element, so theta and s alpha. You can infer evolution equations for s alpha and theta from this evolution for the Cartesian coordinates, and s alpha t comes out to be v alpha minus theta alpha u. So you can compute that. And then this is spatially periodic, so we don't want exactly an arc length parameterization because the arc length of one period changes over time, at least if it were the time-dependent problem. So we actually want a normalized arc length parameterization. So we're going to take S alpha to always equal L over 2 pi, where L is one period of the curve. So that choice defines V because we have two formulas now for S alpha t. We have S alpha t is V alpha minus theta alpha u, which is inferred from the velocity. And if I differentiate S alpha equals L over 2 pi, I get S alpha t equals LT over 2 pi. And I solve for V, I get V alpha is theta alpha u plus LT over 2 pi. And then you can solve for LT also, and really V alpha just comes out to be the projection which zeroes the mean of theta alpha u. So V is basically an antiderivative of theta alpha u. Okay, and the real strength of the Howell, Grubb, Shelley formulation is that the curvature is linear. The curvature in terms of tangent angle and arc length element is theta alpha over S alpha alpha, which then using our formula for S alpha becomes 2 pi over L theta alpha. L is one of the unknowns, but it depends only on time. So spatially, curvature has become linear then, which is much better than if we were using Cartesian coordinates. So the tangential velocity, I said, is enforcing the preferred parameterization, the normalized arc length parameterization. The normal velocity, we don't get to pick. The normal velocity has to come from the fluid dynamics, and the fluid dynamics are the irrotational Euler equations with vortex sheet. They're the irrotational Euler equations, but there is vorticity in the fluids at the interface. There is vorticity concentrated on the interface. So the fluid dynamics really are the normal velocity has to be the normal component of W, where W is the Birkhoff-Rod integral. The Birkhoff-Rod integral gives the fluid velocity in the case of a vortex sheet. So we can write the Birkhoff-Rod integral. I said we want something that doesn't depend on complex analysis, but I'm not really doing complex analysis here. I'm just using complex notation. There is a tiny bit of complex analysis in writing the Birkhoff-Rod integral with a cotangent, but it is minor. But the Birkhoff-Rod integral W1, W2 can be written in this way. It's the principal value integral of gamma, the vortex sheet strength, times the cotangent of differences of the interface position. So gamma is the vortex sheet strength. It's proportional to the jump in tangential velocity across the interface. And we have an evolution equation for gamma. The evolution equation for gamma comes directly from the Euler equations. In particular, since the fluids are irrotational, in the bulk of each fluid, you have a Bernoulli equation for the potential in each fluid, and you can take the jump of those Bernoulli equations across the interface. And that gets you, with a few more steps, that gets you the evolution equation for gamma. So gamma is the surface tension term. Tau is the constant surface tension parameter. And then you get a term just related to the fact that we're using a non-Lagrangian parameterization. W dot T is the Lagrangian tangential velocity, and V is our tangential velocity. So you get a transport along the curve related to that. So this is the gamma T equation if the two fluids have the same density. There are more terms here proportional to the jump in density, which I didn't write, just for simplicity. We can deal with that case, and we can deal with all those terms. Okay, so I said that we were developing a traveling wave ansatz that didn't require the assumption of single valued height. So let's get back to that. Let's get back, now that I've described the equations of motion for this interfacial problem, let's get back to formulating the traveling wave ansatz. So again, the usual traveling wave formulation is to take things to be a function of x minus ct, where c is the wave speed. So we're not going to be doing that. We need to replace this with something. And so we're going to be finding a traveling wave ansatz for a parameterized curve. Well, our traveling wave ansatz for a parameterized curve is that the velocity of the curve is c comma 0. So x of alpha t, y of alpha t is the position of our curve. The time derivative of that should just be c comma 0. So you have the whole curve. It just moves with speed c. Okay, that is our traveling wave ansatz. X of alpha t, y of alpha t, t equals c0. Okay, so then again, similar to what we did with the arc length element, we now have two expressions for the velocity of the curve. One is the traveling wave ansatz xyt equals c0. The other is the velocity of the curve is what we described, that xyt is u times the normal vector plus v times the tangent vector. We also have an expression for the tangential velocity that v was an antiderivative of theta alpha u. That projection p there is just the projection which removes the mean of a periodic function. So the zero mean projection of theta alpha u. So you can solve these equations. In a way, it looks like there are three equations, but three equations for two unknowns, the unknowns being u and v, but they are consistent. It's not overdetermined. The three equations are consistent. So the solution of the equations is that u equals minus c times sine of theta, and v is c times cosine theta. So there is redundancy in this again. The v equation is redundant from the fact that the tangential velocity solves the tangential velocity and forces the arc length parameterization. So really, the tangential velocity is really just about parameterization. This really, you can think of this as one equation, and we need two. We need, again, basically a position equation and a velocity equation. And so this is one equation. U equals minus c sine theta is the first part of our traveling wave ansatz. So we still need a second equation. Okay, so we need a second equation because we're trying to solve for two components of the solution, theta and gamma. So we need a pair of equations in our traveling wave ansatz. So our first equation was u equals minus c sine theta. For my second equation, we're going to take the time derivative of that. And so ut equals minus c sine of theta t. So we want to always be in the u equals minus c sine theta situation. We want that to hold initially, and we want it to continue to hold at future times. And so we're going to take the time derivative of it. Well, if we have a wave of permanent form, then it's going to be the case that theta t equals 0, right? If my whole thing is just moving, then my tangent angle at a point is going to be staying the same. So theta t is 0. So when I take the derivative, the time derivative of minus c sine theta, I'm going to get 0. So my second equation is really just ut equals 0. Well, I had a formula for u. U was the normal component of the Birkhoff-Rod integral, which we can write this way. And now when I take the time derivative here, take the time derivative of this u, I'm going to take the time derivative of theta. I'm going to take the time derivative of L. I'm going to take the time derivative of z. And those things are all going to give me 0. They're going to give me 0 because the length is not changing. The tangent angle is not changing. Technically, z is changing, but I'm subtracting the time derivative of the other z. Z is x plus iy. It's the position of the curve. Zt is equal to c. And so this, when I take the time derivative here, I get c minus c, which is 0. So the only place the time derivative lands is on this gamma. And that formula for ut with gamma t in it, this is a lot like the Hilbert transform of gamma t. It's not exactly a Hilbert transform, or at least it's not exactly a flat Hilbert transform, but it's a lot like the Hilbert transform of gamma t. And so if I say the Hilbert transform of gamma t is 0, it's basically saying gamma t is 0. And that turns out, thinking that way turns out to work. You can see immediately that if gamma t is 0, then ut is 0. The other direction also works. If ut equals 0, we were able to show that gamma t equals 0. So my first equation was u equals minus c sine theta. My second equation is gamma t equals 0. And so here are then the equations of the traveling wave ansatz. These two equations make up my traveling wave ansatz. The first is the equation u equals minus c sine theta, where I've written out what u is in terms of the fluid dynamics. And then the second equation is gamma t equals 0, where I've written out gamma t in the density matched case. You can add more terms here. You can add rho 1 minus rho 2 times a bunch of stuff and get the non-density matched case. But I'm just showing this in the density matched case for simplicity because it's really a lot of terms. Okay, and then all the other quantities there. So the unknowns are theta and gamma. All the other unknowns you see there, like L, V, Z, W, you can determine them all by theta and gamma. L, V, and Z are determined by theta alone, and then W is determined by theta and gamma using the formulas that we've developed. Okay, so that is our traveling wave ansatz that does not assume multi-valued height. And then I said we use that to prove the global bifurcation theorem. And so we do that using an identity plus compact global bifurcation theorem. So in particular, this system of equations can be rewritten as an equation theta gamma plus a compact operator k of theta gamma equals 0. So let me go back to the equations. So this might not look very much like that, but again, I said that this integral is a lot like the Hilbert transform of gamma. So we write the left-hand side of the first equation as the Hilbert transform of gamma plus a smooth remainder, and that equals minus c sine theta. And then we apply a Hilbert transform, and we get gamma plus the Hilbert transform of a smooth remainder equals minus c times the Hilbert transform of sine of theta. And there's another step there that you have to adjust for the mean of gamma. But other than that, this gets you the gamma plus a compact operator equation. And here we have theta right here. So we apply two antiderivatives with respect to alpha, and that gets me theta plus two antiderivatives of this stuff equals 0. Smooth terms give you compact operators, and the two antiderivatives there make this smooth. The smoothness here comes from the fact that the difference between the singular integral and the Hilbert transform is smooth, and that gives a compact operator. And then there's one more issue here, which is here we have theta. You need to substitute the second equation for theta up into that theta to get the compactness. Okay. But we're able to do this. We're able to write the system as theta gamma plus a compact operator applied to theta gamma equals 0. Okay, and so I mentioned here the two steps. The first one is writing U as the Hilbert transform of gamma plus a smooth remainder. And then in the other equation, we invert the derivatives on theta. So I mentioned that inverting those derivatives can be viewed as inverting the curvature to gain regularity. And when we did this, it was pointed out that other authors have done that. I believe there's a paper by Madiok where some smoothness is gained by inverting the curvature in a different formulation for a related problem. I don't know exactly the problem, but okay. So then after making the identity plus compact formulation, some spectral information has to be computed. You have to have odd crossing number, but we get this global bifurcation theorem that you get a lot of traveling waves bifurcating from the quiescent equilibrium, so bifurcating from the flat state. And as is usual in global bifurcation theorems, you end up with a list of a bunch of possible ways that your curve might end. So you could have your curve of solutions might end because you have interfaces with lengths which are arbitrarily long. So the length could go to infinity, the curvature could go to infinity, gamma, which is the jump of the tangential component of fluid velocity, or its derivative could go to infinity. You could end because the waves intersect themselves. And so that's how the Crapper waves end. The Crapper waves have waves with points of self-intersection. You get a pinching singularity and in the Crapper wave. So we could have that here too. And then the other possibility E, which I'm going to talk about some more, is that you could converge to a different trivial state. You might have a sequence of waves whose interfaces converge to a flat configuration, but where the speeds, you have two different possible speeds. Speeds contain at least two convergent subsequences whose limits differ. So, you know, that's a complicated way of saying you have a trivial state, you leave the trivial state, and you come back to a different trivial state. So basically, the trivial state with two different speeds are connected by, you get reconnection to trivial. Okay. Then we have an option F, which is special to only the case when the mean of gamma is 0 and the two densities are equal. I'll probably skip option F. Okay, because I think you can correct me if I'm wrong. I think I'm only supposed to go to about 9:40. So I'm going to try to wrap up in about 5 minutes. So we found 6 possible ways that a bifurcation curve could end here. Typically, when you prove such a result, you want to get more detailed information than that, than just saying, you know, here it's like saying something must go wrong. We have 6 different things that can go wrong. It's not very detailed if we're not saying which one actually happens. So usually in such a result, you try to eliminate several of the outcomes. So eliminating an outcome could mean that it doesn't occur, or it could mean proving that if it does occur, then one of the others also happens. So one of your items is redundant at least. So we haven't been able to eliminate the outcomes. We think, I'm going to show numerics for basically the rest of the time here. And the numerics indicate that all of the outcomes A through E do occur. The only one that doesn't is F. So F was a special case. F was when gamma bar is 0 and rho 1 equals rho 2. That it means the speed can be arbitrarily large. We have not observed the speed becoming arbitrarily large in that case. So F is the only outcome that we have not observed, but we can't rule out. Okay, so here's some computed solutions. So this has non-zero gamma bar, and the two densities are equal on the two sides. And you get something that looks like a Crapper wave, right? So that neck there is multi-valued. And you might not, I think you can believe from this picture that the height is multi-valued, but here's a close-up of that interface. And so you very clearly see the 3 intersections with a vertical line, just like in the case of the Crapper wave. Here's another traveling wave. This one is a water wave. So here the upper fluid has density 0. This is a large amplitude capillary gravity water wave. And again, in pockets like this, you have multi-valued height. And again, to see it, a close-up of the interface, on a vertical line, you do get the multiple intersections. Okay, so I said outcome F was the one we don't observe. That's the case rho 1 equals rho 2 and gamma bar equals 0. In this family of bifurcation curves, that's the uppermost curve here. So this one here. And this is a graph of speed on the vertical axis versus amplitude on the horizontal axis. Outcome F was that the speed could go to infinity, but we don't see that. We see the speed leveling off at an asymptote and the amplitude growing. So we don't see outcome F. Okay, outcome E we think is the most interesting. This is the reconnection to trivial outcome. The reason we think this is the most interesting is that this does not occur for pure gravity waves. For pure gravity water waves, you can do a maximum principal argument to eliminate this outcome. You can say that this reconnection to trivial does not happen for pure gravity waves, pure gravity water waves. With surface tension, you don't have that maximum principal argument, so it hasn't been clear if you've been able to rule this out. And we say you can't rule it out because we can observe this. Now, we only observe it numerically, but we think this is pretty strong evidence that this outcome actually happens with surface tension. The one quirk of it is we only see it happening with negative gravity. So if it can be ruled out for positive gravity, then it's going to be a very particular kind of argument. It would be nice if that could be done, but yeah, it's going to be a very particular argument. It's not about counting derivatives like the maximum principal argument was. It's going to actually be about the parameter values. Okay, and with my PhD student, David Soulon, we've been able to generalize all those results to hydroelastic waves. I say all those results, meaning the numerical results and the global bifurcation theorem. We have two papers, Ben Akers, David Soulon, and I, on hydroelastic waves. So this is a model for free surface flows with elastic effects, such as ice sheets on the ocean, using a model of Tolan and Plotnikov. And so we can repeat the global bifurcation theorem, and we can repeat the computations, and we're able to get very complicated multi-valued height structures, more complicated than what we had in just the surface tension case. And finally, I'll say extension to 3D. The philosophy certainly extends to 3D. The traveling parameterized curve philosophy absolutely extends to 3D. There's no reason you can't do that. You can't make the formulation. There's no reason you can't make the formulation. So you can do that. It's been done once. Ben Akers and Jonah Rieger computed 3D traveling waves. They did not use the Birkhoff-Rott integral. So this is a model equation using basically Riesz transforms in place of the Birkhoff-Rott integral. And that's because it's hard to compute the Birkhoff-Rott integral in the 3D case. Mike Siegel and Svetlana Tulipova and I have work doing that. But we use this cotangent trick, which I said was a little bit of complex analysis, to write the Birkhoff-Rott integral in the 2D case. In the 3D case, that cotangent trick isn't available. And so numerically computing the Birkhoff-Rott integral in 3D is computationally intensive. But they did use, Akers and Rieger did use the traveling parameterized curve philosophy in 3D. And so then for 3D, working on analysis for the 3D problem with the full velocity, proving a global bifurcation theorem in that case, is joint work with Doug Wright and me and Miles Wheeler. Okay, that's what I have for you. Thanks.
Thank you very much, Dr. Ambrose. Very nice, interesting, very interesting talk. Thank you very much. Okay, so now let's open questions and comments from the audiences. Any questions or comments?
Yeah.
Yes, please.
Yeah, so you said that you had a wealth of information on the linearized operators, and so is there on the spectral properties of the linearized operators, do we have some special behavior when the graph the surface is not a graph?
Uh,
Change.
so uh, the question of whether it's a graph or not doesn't really matter in the method. Everything's done for the tangent angle, and you know, like for the Crapper wave, the book of Okamoto and Shoji uses a formulation of the traveling wave equation for the tangent angle with a special parameterization. And in that Crapper case, they're able to, I think, compute eigenvalues of the linearization around a Crapper wave, and you know, look at the kernel and the range and the co-kernel and everything very explicitly. For the global bifurcation theorem, we needed to compute the crossing number of the linearization, crossing number of eigenvalues of the linearization, and yeah, there was no effect there. Again, everything's in terms of the tangent angle. So whether the surface is multi-valued or single-valued, whether the height is multi-valued or single-valued, it's really invisible to the formulation. It doesn't matter. In the surface tension case, computing the crossing numbers involved, because surface tension is a second derivative of the tangent angle, it involves solving quadratic polynomials. In the hydroelastic case, you get two more derivatives. So instead of a second derivative of tangent angle, you have a fourth derivative, which means you have a second derivative of curvature. And that involves solving some quartic polynomials. And fortunately, the quartic polynomials, you know, that can be tricky, but they had some structure that was able to be figured out by my student David Sulon. But yeah, there was no change that I'm aware of. There's no change I'm aware of in the spectral information on when the interface transitions from being single valued to multi-valued.
Okay, thank you.
Okay, thank you. Any other questions? Okay, then my next question, it's are you assuming the symmetry of the shape?
In most of the work, maybe in all of the work, yes. The global bifurcation theorem and the Crapper wave solutions also, yeah, the function spaces we use, you know, when you formulate your global bifurcation theorem, you have to say that the operator maps from some function space to some other function space. We build the symmetries into the function spaces. So, you know, the operator might map from even L2 function or even H2 functions to odd L2 functions or something like that. So the symmetries of the waves are built into the theorems. Yes.
Okay, thank you. And also, can we say something about limiting form from this theory?
Not from the theory, only from the numerics.
Okay.
Yeah, we you know, some of these graphs that we have are the limiting forms. You know, overwhelmingly the limit happens because you reach a self-intersection, but we can only say that numerically.
Okay.
Yeah, we don't have a theorem about which limiting form occurs or real structure of the limiting form. I did mention that it does appear, you know, it does appear that the limiting form typically has an additional symmetry that the waves did not have during most of the bifurcation curves, but we don't have a theorem on that either. That's only
numerical.
that's
Okay.
also.
Okay, thank you. And the last question is about, I think this is maybe this is my misunderstanding, but I was thinking Bark-Float integral is derived using the Cauchy's integral formula. So I was thinking only for 2D, but can we extend that integral for 3D case?
Yes, the Birkhoff-Rod
really?
integral, you still have in 3D. There's sometimes I've wanted to look at a derivation of it. There's a paper by Kaflish and Lee,
Mhm.
paper by Russ Kaflish, where they derive a Birkhoff-Rod integral in 3D.
3D.
You know,
Okay.
so
I have
another
to
way
do that.
I would say it is it comes from the Biot-Savart law. So the Biot-Savart law for
it's
for
connected. Ah.
finding velocity from vorticity. So you still have that the vorticity is a Dirac mass, right? The fluids are irrotational in either phase. So there's no vorticity most places, but you have a jump in tangential velocity across the interface. So your vorticity is going to be a derivative of that jump. So the vorticity is a Dirac mass. So you put that Dirac mass into the Biot-Savart law. That can get you the Birkhoff-Rod integral.
Okay. Thank you very much.
But for a specific derivation of it, yeah, I usually look at a paper by Russ Kaflish and Lee. I'm not sure what Lee's first name is.
Okay. Okay, thank you very much. Any other questions? Okay, thank you very much again for your contribution.